right, so welcome to this presentation. In this presentation, we are going to show you an end-to-end machine learning process. These are going to be the 23 best machine learning practices that all and every machine learning developer or expert uses to get their data, train their model, and deploy their model into production, and even do monitoring and governance at the end of the process. So this is a comprehensive guide to production machine learning. Hey everybody, my name is Emmanuel Achayo. I'm a research analyst at a community college in North Arizona. That's in Flagstaff here in Arizona. All right, so the first step when building machine, of course, we know that the whole process of machine learning is just to answer a business question or try to solve a business problem or come up with a business use case. And then we develop models which are going to be used to try and answer these business problems. So, of course, before we do anything else, before we even touch the data, before we even build a model, we need to understand what is the business problem we're trying to solve. So what's the business problem definition? So in this, you're going to try to improve a decision. The whole thing here is to try and improve decisions, not just accuracy. So we spell out the business process changes when the model acts. And most importantly, we want to decide if the problem truly needs an ML model, or is just something that we can do via some histograms or some simple visualization or dashboard to show us how to deal with the problem. So let's say, for example, you were trying to help small clinics to deal with claims denial from insurance firm. There's a big problem in clinics when they submit their claims and the insurance company denies their claims or they are underpaid for their claims. So if that is the problem that we are trying to answer, the whole thing problem we're trying to solve is, can we help small clinics to solve this problem before it reaches the insurance company? Because what happens is the clinics always submit these insurance claims to the insurance company with errors, or sometimes with inconsistencies, or sometimes just having a wrong ICD-10 or CPT coding. The ICD-10 and CPT coding, for those who don't know, are medical codings they use to determine disease or diagnosis. So it's always very long codes, and there are always some extensions or additions to these codes. And sometimes the people doing this just get it wrong. Or the small clinics don't just have the staff to do this. So it could be really helpful if we can give them a model that can help them to identify the mistakes or the problems or the errors, or in general, just the claims that probably are going to be denied. So we identify this before it's sent. And then the model is, if possible, the model is able to correct this. And then maybe there's a human in the loop who helps to verify this, then they send it. That way, we are able to increase their revenue, increase their processes, and even increase in service delivery. And of course, that brings us to the next thing you need to do, the next step in a machine learning process is business metric translation and success metrics. So here we're just trying to turn better prediction into money, time, and risk saved. So we're just trying to help, for example, for this particular problem of helping small clinics to deal with denial claims, we're trying to help them get more money. Of course, when they get more money, they can get their time back, and they can also deal with some risks in the process. So you must know what will determine success for us. Is it going to be some revenue change, some maybe time saved, or maybe increase in the business processes and stuff like that? And then, of course, the last thing here is to just come up with some guardrail metrics, some fairness, latency. Latency just simply means how quick this thing is going to be done, or how fast it's going to be done, how slow, fast, and then the costs. So the cost is a lot of things. It can be the cost of doing the business, but when it comes to machine learning, it's mainly the cost of setting up the infrastructure and the tools you're going to use to do this. Guys, loving this so far? So that is the business side of it, where we determine the problem, and then we determine the success metrics. Then once we know the problem and we know how we're going to define success when we reach it, then now we go to data, all right? Because it's data that is used to train models. There's several types of data. There is tabular data or flat data. There is you can use images, videos, whatever. But before you get to that, let's look at data collection and acquisition. So under data collection and acquisition, we list every data source. So where are you going to get the data? Are you going to get it from a database, from an Excel file, from an API, or from some logs? And when you're doing this, we need to note who owns the data. How was the data collected? How is it updated? Did they follow some ethical rules to get this data? And such questions you really need to ask yourself early enough, because you don't want to develop a model with some data, then you take it to production, and then when ethical board comes in, or people doing governance and maintenance or monitoring, they realize that the data that you used was not ethically collected or stuff like that. So, and of course, you keep a lineage record for raw import to cleaned data set, which is critical for audits and debugging. All right, so now we're in the data phase. We're collecting data, we are doing data acquisition. The next thing is data validation and quality checks. So we determined our primary business use case or primary business problem we're trying to solve. Now we need to validate the data that we have. Okay, now we have the data, cool. Is the data going to answer that particular question, right? So here, one thing you must understand, and this is a rule which everybody should work with, is bad data ruins good models. Really have that in mind all the time. So you need to check for column types. Are the variable fields going to help us answer the questions? Are there valid ranges, missing values, duplicates? And in doing this, you also want to compare today's stats with last month's stats. For example, just to spot some drifts. Imagine you're dealing with sales data, and we all know that sales always just goes up between the last quarter of the year, the last 3 months of the year, right? And then they just tank the first quarter of the year. So if you're dealing with sales data and you're trying to predict how sales are going to be in January, it is using data for the last 3 months of the year. That data is not going to match so well with January, because there'll be some data drift between the each quarter of the year. So because there's always for sales data is always seasonal. There's always seasonality allowed when it comes to sales data. So you want to make sure this drifts between the previous data and the data you're using right now, especially if it comes to things with seasonality. And then we have automate tests so that broken data never enters training. So now we're still in the data stage. Now we've done some data validation. Now we need to do data labeling. Now data labeling is mainly for supervised learning. So there are two types of learning when dealing with machine learning. There is a supervised learning and the unsupervised learning. So what's the difference between these two? Now, supervised learning is mainly when we are labeling data. Let's say, for example, we're trying to train a model or an algorithm with images of cats and dogs. So we give it images of cats and dogs, and we've already labeled, this is a cat, this is a dog, this is a cat, this is a dog. So with every image, it's already labeled, right? So the data learns from already labeled data. So you can give it 500 images of cats and 500 images of dogs, and then it knows like, oh, if it looks like this, it's probably going to be a cat. If it looks like this, it's probably going to be a dog. So then to test this data, we're going to give it other images which are not in the first data that we gave it to learn from. We're going to give it an unseen data or an unseen images of other cats and dogs, and then we feed it. We already know as human beings that this is a cat and this is a dog. So we're just trying to test, hey, can it get it right? And then you feed it. So that's called labeled data. Now the unlabeled data is when mostly you're using things like tabular data or flat data. Like for example, in our claims denial model or problem, we're giving it data and trying to tell you, hey, we don't know what's going to happen in the future. We don't know which one is going to be denied or not denied or accepted. So you tell us from this data. So that's called unsupervised learning. So if it comes to data labeling, after data validation is you train with labeled examples, define exactly what positive means. So if it's, for example, the claims denial, you must really define precisely that positive is going to mean the claim was accepted, negative is going to mean the claim was denied. And for the people who are doing labelers must be trained well, and you must spot check their work and measure agreement. Like if somebody is labeling data, we must know that this person is always consistent throughout when he's labeling the data. And then you do something like balance classes or applying weights if one label dominates. So in the last sentence here, it just means, let's assume we are giving our model data on claims denial, and 95% of this data is just claims accepted. There's going to be some risk of overfitting where with every prediction that the model is going to make, because it learns so much from claims accepted than claims denied, it's going to be more biased in predicting every claim is going to be accepted, because very few data that we gave it to learn from were denied. So to balance this off, we apply weights during model training, But also what you can do is we can give it, just make sure that you balance the data such that you have almost an equal amount of claims denied and claims accepted. That way the data lands properly. Okay, I hope that makes sense. So the next one is data cleaning and pre-processing. So we are in the data stage now. We're still in the data stage. We've dealt with the problem, the business problem. So we've acquired some data. We've validated the data. We've done some data labeling if it's supervised learning. Now that we have the data, let's clean it up. Now this data, because you can't clean data which you don't know if it's going to help you, right? That's why you acquire the data first. You validate it. Is it going to help me? Yes. Okay, now let's clean it and pre-process it. So here it's very simple. It's just the normal cleaning. You look for errors, inconsistencies, outliers, and stuff like that, just to clean the data. So fix mixing or wrong entries with clear rules, not guesswork. Normalize or standardize features, only if your algorithm needs it. And save every transformation so you can apply the same logic during prediction. So the last statement here, save every transformation, is if you're going to transform some data, say you're going to do encoding, say you have a continuous variable, say age. Age is a continuous variable, right? But because it's continuous, you want to make it categorical. We can say between ages 0 and 18 is 1, between 18 and 50 is 2, and then 50 and above is 3. So you can do this encoding, or this transformation, this data, and then create a new feature or a new variable called age category or age cat. But when you do this in the data before training, which is going to be used for training, we must also make sure that in the schema, we use the same logic in prediction. So that when the data comes in, when data will coming in at production, we don't expect categorical age we don't expect continuous data, that is age category, to come in. We expect it to come the way it was categorized during training. Okay, so that's what they mean by same logic during prediction. All right, so data cleaning and data preprocessing. The next step is exploratory data analysis, EDA. So this is just the basic visualizations you can do to data, getting things like mean, standard deviations, medians, drawing some visualizations, some graphs like histograms, box plots, pie charts, to just see the distribution of data. So we are trying to understand data before we model. Plot distribution, correlations, and outliers. Then we identify which variables truly relate to the target and which leak future information. Now, sometimes they say EDA reveals model isn't even needed, right? Remember when we're defining business problem, we said that sometimes when, as a data scientist, we might go in, start to build a model, but then realize we don't need to build a model to solve this problem. This problem can simply be solved by some small data visualization. So sometimes the EDA reveals that we don't need a model. All right, so we are still inside our data. We are validating it, we are cleaning it, we are exploring the data. We're trying to see everything around the data we're going to use for our modeling. The next step, of course, once we're done with all this data thing, we now have a good, clean data, well structured, if we have done some transformation in it. Now we need to do some base model establishment. This is where it starts getting interesting. So now we've realized that the only way we can solve this business problem is when we develop some model. Awesome, cool. Okay, before we go deep into more dense or more advanced models, let's just do some baseline model establishment. Now, for those who are new to this, the baseline model can just be things like simple linear regression or simple logistic regression models, right? These are the simplest relationship models that anybody can always use to get relationship between data or outliers or outcome input and outcomes. So always start simple. A logistic regression or mean forecast sets a benchmark. So mean forecast is just using averages to forecast the mean. If the average sales for December of this year, maybe December of last year we sold 1 million this in December of last year. Then if that was the average for the past 5 years, then we could say that, okay, probably this year it's also going to be around $1 million. All right. So the last statement here says, if your fancy deep model can't beat the baseline meaningfully, stop and reassess. So baseline keep you honest and measurable. So we are moving on quite well. We have defined the business problem. We have our data is clean. It's validated. We have picked our baseline model. Now the next step here is data flow and infrastructure. So now we have our baseline model, we have our data. Let's get some infrastructure, some data flow. How is data going to flow? Because machine learning model is all about steps from end to end. So let's create how data is going to flow. In data flow, we decide how data moves. So it can be manually or through tools like Apache Beam, Airflow, or data flow. So we also set up things like storage buckets and databases. So buckets are just like where you can store data. And then we set compute like VMS, GPUs, and containers. So containers are like the Docker containers where we input all our codes, dependencies and stuff like that in the container. And so it's good to separate development and production environments and automate builds for repeatability. Now, under automating builds for repeatability, for instance, we have MLOps. For those who are not familiar, the term MLOps is just machine learning operations. It's like DevOps, development operations for software engineers. So the MLOps are the ones we use to automate the pipelines and the infrastructure. We're probably going to talk about this a little bit more in the next steps. And so the first 9 steps so far, very simple, nothing much, nothing fancy, just some simple normal things that people do with data. All right, so the 10th step is feature engineering and selection. Now, if there's one thing about modeling is this. This is like the most important thing. If modeling is 100%, then feature engineering is like 80% of the work, okay, of modeling. Because feature engineering is where you really get to work with the variables or the fields that are going to really determine our outcome or our prediction. So here I need some domain expertise, people who are experts in this, because you're going to do some So feature engineering is about working with variables, building new smart variables that can help us even make better predictions. So when we talk about features, just think about variables, okay? But mainly it's about smart variables. So we build new variables from already existing variables. So craft inputs that capture domain insight. You can do things like ratios. So for example, for the sake of the example that we took at first, like claims denials for insurance companies in clinics, a ratio can be the ratio between claims accepted and claims denied, or claims denied over total claims submitted, right? So that can be a good piece of feature that we can add as a column or as a variable to our data set. That way, the model even learns better. Can be trends, can be time lags, and categorical counts. Then we need to test each feature's value and remove noise. And simpler, faster features usually outperform messy complexity. So even as we develop these smart variables or features, let's not make it so complex. Complexity just makes the model not perform well. All right, then what's the 11th step in machine learning model? So the 11th step in machine learning model is data pre-processing pipeline. So in a data pre-processing pipeline is where we create one reproducible pipeline for training and inference. So a pipeline is just like a plumbing pipeline. Think about it like just things moving from one stage to the next stage to the next step. So we have components in the pipeline, and then data just flows or information flows from one step to the next. And then we have to version every transformation. So the version is just important when we need to do things like rollbacks, and version is also important just to keep track of, okay, what changes have we been doing over time to our data and our processes. That way we can always, if there's an error or if we did some update in our new version and then we deploy to production and realize, oh, this has a mistake, we can roll back to the previous version. So version every transformation, so the production data flows identically to the training data. You need to test it. One mismatched step can break prediction later. So now at this stage, mostly we're doing setup of the infrastructure, right? Then number 11 is model selection and architecture design. Now the first one, remember, we set a baseline model just to see how the data works with the baseline model or how it lands with baseline model. Now in model selection now, this step number 12, now we have to decide, it's like the next level of modeling, right? We had a baseline model. Now let's be a little bit more specific. Several machine learning platforms like Microsoft Azure, Amazon SageMaker, Google GCP, and the others, they provide model guidance where you can just go and pick a model and use it to train your data. So here you pick models suited to your data. So here's some of the models you can pick. So models are just algorithms, right? that machine uses data to learn from and, of course, help us in prediction or do something. So we have different types of models. We have tree models, logistic. We talked about logistics and linear regression, transformers, RNNs. I'm forgetting what RNNs is, prophets, and LSTM. So these are all different types of models. So tabular data, you might probably use things like tree models, or logistic regression. For text, you're going to use transformers or RNNs. For time series, you're going to use prophet or LSTM. So when you're choosing these models, we also need to balance accuracy with interpretability, speed, and cost. The third step, this is getting so nice actually. We're almost halfway through there. It's also another very important part of it, which is setting hyperparameters. So hyperparameters are just configuration settings that you do before training to ensure that the model trains properly. Okay. So some of the hyperparameters here are things. It's just like a knob. Well, think about like having that traditional transistor radio where you had knobs and you had to keep on turning this knob to get a clear audio or clear transmission from your favorite radio station, right? So it's the same thing. You're having knobs. You keep on twisting these knobs to just make sure your transistor radio is much more clear. Just that in machine learning, it's mostly a chord or a button that you press, right? And there's several buttons sometimes. Yeah, it's not like just one knob. So in hyperparameter setting, we can tweak around things like with things like learning rate, epochs, which is the number of iterations or the number of times the data passes through the model. Things like the number of layers of neurons, also tree depth, etc. So, and then the different structures you can use grade random or Bayesian. Now, Bayesian is like the hybrid of random and grid. Random and grid have some weaknesses, I'll say, or shortcomings. But Bayesian is like the hybrid of the two. So most always pick Bayesian for structured searches. And then we want to limit trials and always log results so you can reproduce any run. Now, if you notice something that is common about this is logging and documentation. The whole process you must log and document the steps of the process you follow, from picking the data to validating the data. Which steps did you follow? Which logic did you follow? This one just easy to reproduce it and to make changes in the future if you need to. And where maybe the whole system broke, right? All right. So that is number 13. We set hyperparameters, and then number 14, model training and cross-validation. So now we do the real training. So we have our data. We've chosen our model. Now let's train the model and validate model. So cross-validation here is mainly we're going to train different models, and then we're going to compare which model gives us the best result. So you split your data properly, e.g. time-based if it's sequential. Use cross-validation to see how models generalizes. So which models? You can pick maybe 2 or 3 different models, and then we see which models really gives us better generalization or better outcome. And of course, we want to track the metrics and artifacts in a run log for transparency and rerun. So again, logging all the time or documentation is very, very key. All right. I hope you guys are enjoying this. Number 15 is model interpretation and explainability. So now we have our models are also running. We are training our models. Let's interpret it and explain it, right? Because if you can interpret what our model is doing and explaining how our model is helping our businesses or our clients to save time, increase their revenue, or increase their service delivery, then there's nothing our model is doing. At the end of the day, we are building these models to help businesses be more efficient, provide better value, better services, or better products to their customers, and also to, of course, increase their revenue. So here we explain what drives prediction. Global tools. So we have global tools and local tools. So global tools show features, matter overall, and local tools show why one record got its prediction. So document reasoning. Again, documentation logging, very, very key, is especially in regulated domains. All right, so our model is starting to run. We're trying to come up with some prediction and explainability methods. Now let's validate, evaluate, and test our models. So this is like the meat of model development. We must validate, evaluate, and test our model. So what is validation? Validation is simply you train a model. So picture this. You get the students into a class, you train the students, or you teach them a course. say for 2 weeks or 3 weeks. Then you give them a quiz, and then you see, hey, how are we performing this quiz? Then after that, you go and teach these students for another 2 weeks or 2 months. You give them another quiz. You see how they perform the quiz. Then at the end of the semester, you give them now the final test, right? Like, okay, here is now a test. Let's see how are you going to perform this test. It's the same thing with models. So validation here is just giving them the quiz. You give the model, okay, the model has now learned from our data. Let's take a data which is similar to what they learned from, but they haven't really seen it. And let's see how it performs into this, okay? And then the model, you give the model does its prediction. And then evaluation is when you come and see, okay, how did the model perform in our quiz, right? So you evaluate it. And then test, of course, is now the final thing. Even before you take it to production, now you give it a lot of unseen data to try and predict or try to do what it's supposed to be doing. So that's called testing. So that's what it's all about when it comes to validation, evaluation, and testing. So here you're going to measure accuracy, recall, and precision. And the good thing about some of these tools that we use to develop models is they have a feedback loop. Like they tell you, hey, this is how your model is performing. This is the accuracy, this is the precision level, this is the fairness level. So they even give you charts to see just how it's performing, recall and prediction test and stuff like that. All right. So that's on validation, evaluation, and testing. The next one is adjusting hyperparameters. So of course, as we do validation, evaluation, and testing, we are going to be seeing the metrics. How is it performing? We are checking its accuracy, precision, and recall. We need to adjust the hyperparameters. Now, if you didn't get the first time, let me repeat what hyperparameters are. So hyperparameters are just configuration settings that we do to the model to help it learn better. Okay? And the hyperparameters include things like the number of layers in the neuron, epochs, and learning rate. So you always want to adjust these hyperparameters once in the process of validating, evaluating, and testing your model. But you want to do this one at a time because you don't want to test all of them at the same time. So you can decide, let me adjust a little bit of the learning rate and just see how good is the model getting to what we need to do. So we use error analysis to see why prediction failed, then tweak hyperparameters accordingly. We make small tracked changes. But then we must know when to stop because sometimes models overlearn. So stop when extra tuning doesn't improve the business outcome. I love this. So now we've adjusted hyperparameters. Let's do business validation and impact assessment. So now let's assume we tested all the hyperparameters. We have ensured the model works perfect, or at least as we expect it to work. Let's do some business validation and impact assessment. So we're going to translate metrics gains into actual impact. Money saved, patients' help, time reduced. So now the model is supposed to, we're going to see if the model really does what it's supposed to be doing. So we run pilots or shadow tests to see if staff trust and use the model. That's so important. So there's so many things around building the models. And then we have to secure sign-off from business stakeholders before going live. The ninth step, and we are almost getting to the end of this, the ninth step in machine learning is model packaging and registry. So again, documentation, logging, registry, whatever, all these things is about just ensuring that when somebody looks at our documents or our logs, whatever, they can see everything that we did. So we need to bundle your train model, your preprocessing code, and input schema together. So schema, when I talk about input schema, just think about data dictionary. But data dictionary now for models, right? So store versions and metrics in model registry, like Vertex AI model registry or MFlow. So this guarantees reproducibility and traceability. It's all about reproducibility and traceability during logging and documentation. Then the 20th step is A/B testing and gradual deployment. So under A/B testing and gradual deployment here, don't unleash the model on everyone at first. So we do what we call canary rollout. So for those who are not familiar with canary rollout, it's like the long time ago, before we had a lot of tests to test whether a gas was poisonous or not, these people used to use what you call canary. So in a canary, they used to have these birds inside. There are small cages of birds. They put the bird inside and then they put it somewhere where there's a gas, because they didn't know whether the gas is good or not for them. Let's say that it's a mining place or an industry where they produce so many gases. So they put the bud inside there, then in a cannery, then they pass the gas through the cannery. And then how the bud reacts will tell them whether it's safe for human to also be around there or not. Now, it was basic, it was rudimentary, it was not the best way, but by then it was the best way they could know whether a gas was poisonous or not poisonous. So it's like, cannery rollout is just rolling out the model to a small group of users before you roll it out to a larger group of users. It's just like pilot testing. Just roll it out to a small group of users. It can be staff, it can be a small group of users to just see if this thing is performing well on deployment. And then we compare against control. And as like we said before, we must always have some rollback mechanism just in case it doesn't work in real production. We can roll back to the whole thing to see where the problem was. The 21st step is pipeline automation, which is continuous integration and continuous development through what we call MLOps. And I explained MLOps before. It's like DevLops, but just now in machine learning. So during CI/CD, we automate repetitive steps. So all those steps we've developed, we've now ensured our model works at least near what we want it to do. Now, we don't want to keep on writing these codes over again. We don't want to keep on going through the steps over and over again, or keep on manually feeding the data. So what we do is we automate this through MLOps, continuous integration and continuous development. So automate repetitive steps like data validation, training, testing, deployment. So we use tools like Jenkins, GitHub Actions, or Vertex pipeline to keep code and configuration set separate and secure secrets properly. The second last step you want to do, which is very, very important, this is on governance, is model monitoring, governance, and exploitability. So once deployed, you track model performance, drift, and data quality daily. We see, because data changes, and one thing you want to know about models is almost 80% of models that are being developed don't see the light of day. They don't get deployed into production. One of the main reasons is because ground data is always so different from training data. Because ground data is never clean, it's never perfect. But the training data is always very clean because you've done so much around the training data. So we need to track model performance to see is the model performing well over time. As data is coming in, the model is still doing what it's supposed to be doing. What is the accuracy? What is the precision and recall and stuff like that? And then you log every prediction and its rationale for audits. And then, of course, at least with GCP, they always have alerts to just tell the developer of when things change in the model. The final part here is, I don't know why that came before that. That's weird. I think I probably didn't arrange them well. But the final step in model development is model retraining and maintenance strategies. Again, because data keeps changing, we must keep on retraining our model. So we plan how the model is going to evolve. We define triggers for retraining. So when new data comes in, drifts, time intervals, you can decide we're going to train data when new data. We can decide to retrain our models when new data comes in. We can decide to train our models when you have drifts between what you expect and what we had. We can decide to retrain our models during some given time intervals. Like I can say we retrain our models every 3 months or every 2 weeks. And then we keep a feedback loop for updated levels and retire old versions gracefully. So that is the entire steps we follow from start to finish when we are developing our models and deploying them to production. Now, if you enjoyed this, please be sure to support your boy here. Now, this step seems to be, of course, so many steps, but it's not. I've just broken them down into small components that you can for ease of understanding. But for most people who teach machine learning models or use machine learning models, they always bundle these things together. Like they can bundle the first 5 steps into define the problem, the next steps into data validation, and the next step into model development and training, and then the last one is always more maintenance, monitoring, and governance. But this is the entire end-to-end process of machine learning. And you can use this in almost all machine learning platforms out there. Now, stay tuned for our next videos where we're going to also delve deep into now the real tasks of developing this, now the practical bit of it. But have this in mind every time you're going to do that. We're probably going to use, these are the exact steps we're going to use every time we're developing this. So in the next video, you're probably going to look at the actual steps. So stay tuned and please make sure to watch that next video.